Welcome, my name is Spyros Zigouris. I am a computer science professor and you are on videolearner.com. Through this channel you'll find complete lessons and explanations for the International Baccalaureate Diploma program in computer science. Now let's proceed to the next lesson that will be focusing on key differences between CPU and GPU. We are going to deal with design approach and areas of use. First, the design approach. The architectural philosophy of CPU centers on maximizing versatility and computational generality, enabling efficient execution across diverse instruction sets and data types. Furthermore, CPUs are optimized for minimal latency, that is to say, minimizing wasted time, prioritizing rapid sequential task processing even if it's just one task at a time. To ensure high responsiveness in general-purpose computing workloads, SISD single instruction single data is a CPU architecture where a core executes one instruction at a time on a single data element. The emphasis on flexibility, general-purpose capability, and low latency leads to architectural choices where CPUs incorporate fewer cores than GPUs, but each core is significantly more powerful. These cores feature larger cache memories and complex logic units, enabling efficient handling of diverse and complex instruction sets. Another key architectural element in CPU design is advanced branch prediction. CPUs are highly optimized to anticipate the next instruction in a sequence and prefetch it before execution. Now let's see how it works. Suppose we have a 4-stage pipeline where S1 equal fetch instruction, S2 equal decode and calculate effective address, S3 equal execute instruction, and finally S4 equal store results. As you can see, the CPU doesn't wait. Suppose that we are running a program with an if-then-else structure. A branch predictor, a digital circuit inside CPU, tries to guess which way a branch will go before this is known definitively. So CPU starts fetching and executing instructions down the predicted path before it even knows for sure if that path is correct. This is called cache prefetching. In that way, we don't have idle cycle. Now have a look how it happens. 4 instructions are waiting to be executed. Step 1. The S1 instruction is fetched from memory. Step 2. The S1 instruction is decoded. In the same step, the S2 instruction is fetched from the memory now. Step 3. The S1 instruction is executed. In the same step, the S2 instruction is decoded, and the S3 instruction is fetched. Step 4. The S1 instruction's results are written back to the register file or memory. Now the S2 instruction is executed, the S3 instruction is decoded, and the S4 instruction is fetched. Step 5. The execution of S1 instruction is completed. In the same step, the S2 instruction is written back. The S3 instruction is executed, the S4 instruction is decoded, and the S5 instruction is fetched. Step 6. The execution of S2 instruction is completed. The S3 instruction is written back. The S4 instruction is executed, the S5 instruction is decoded, and the S6 instruction is fetched. Step 7. The execution of S3 instruction is completed. The S4 instruction is written back. The S5 is executed, the S6 is decoded, and the S7 is fetched. Step 8. The execution of S4 instruction is completed, and so on. Take a look that in that way, with branch prediction, we don't have idle cycle. This predictive mechanism reduces pipeline stalls. Ensuring that the processor maintains continuous operations with minimal idle cycles. Lastly, instruction set versatility plays a crucial role in CPU architecture. CPUs are engineered to support and efficiently execute a wide and complex range of instructions, which enables them to run diverse general-purpose applications such as web browsers, productivity office software, and various types of games, although they are not optimized for the intensive graphics computations required by high-end gaming. Now, GPUs are architected for high throughput and excel at workloads that can be broken down into numerous smaller, independent tasks. Each GPU core is simpler and less powerful than a CPU core, but is optimized for executing straightforward operations, in other words, simpler tasks, but in parallel. This design enables GPUs to handle large amounts of data simultaneously. GPUs primarily utilize a single instruction multiple data model, the famous SIMD model, applying the same instruction simultaneously across multiple data elements, that is to say, at once. Furthermore, GPUs architectures emphasize efficient data transfer between cores and memory, favoring high memory bandwidth over complex logic components in each core to maximize parallel processing performance. For the end, let's have a look into the areas of use of a CPU and a GPU, or in other words, their usage scenarios. CPU usage covers tasks like running operating systems and supervising system resources, executing general-purpose programs, decoding and managing user actions like mouse clicks and key presses, and finally switching between multiple applications, that is to say, multitasking. On the other hand, usage scenarios in GPUs include processing graphics and rendering images, and video for gaming and video editing, accelerating scientific simulations and machine learning algorithms, encoding and decoding video streams, and finally cryptocurrency mining. And that's all for today. In the next video, we're going to deal with core architecture. If you enjoyed this, feel free to like or subscribe. It really helps the channel. Bye bye.